Okay, so today we're going to expand on what we've been doing the last few days. We're going to talk about trig ratios on the Cartesian plane. I want to see if I can make the time of this video a little shorter than the other ones. I apologize for making them too long, so I'll stop blathering on. Let's just talk about what today's plan is. Uh, Again, we're going to loosely follow the note booklet problems. You may want to have it downloaded and ready to review or take your own notes, whatever works. We're going to expand on what we learned about the unit circle in general and apply it to the Cartesian plane as a whole. So the questions for today are: how do sine, cosine, and tangent of your angle relate to the coordinates of your unit circle or on the Cartesian plane? So in other words, how do those sine, cosine, tan ratios affect your coordinates, and vice versa? How do your coordinates affect those ratios? Also, we're going to look at what are the values of sine, cosine, and tangent at 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees, which of course in radians is 0, pi over 2, pi, 3 pi over 2, and 2 pi. We're going to talk about what the values of sine, cosine, tan are at those points. We'll also unveil the biggest secret in all of high school math. Stay tuned. You're going to see exactly what I mean in a few minutes here. Just another quick reminder, check your email daily and respond to my emails that I send. Again, it's an expectation on us teachers to be contacting you guys 3 times a week. If you're not responding to my emails, that kind of plays my hand. That means I have to now call you guys and actually speak to you over the phone. So again, please check your emails. That's probably the quickest and most efficient way of doing this. But again, if need be, I will be making those phone calls. Anyway, let's start. Ooh, too far. All right, here we go. Trig ratios on a circle. Recall that on a circle, sine theta is opposite over hypotenuse, which again, on a circle would mean that you have y over r. This picture is a really good example of that, of course. If this is your angle theta, y, of course, is this side. That's your opposite side divided by your hypotenuse, which is, whatever the radius of your circle is. In this picture, it was 1 because it's a unit circle. So again, if it's a unit circle, r is 1, so sine theta equals y. This is probably more useful than just saying sine theta equals y, but whatever floats your boat. Cosine, of course, is adjacent over hypotenuse, and adjacent on a circle would be this side right here. So in other words, that would be your x. So x over your hypotenuse, and hypotenuse is, of course, the radius of your circle, but if it's a unit circle, r is 1, so cosine theta is x. Tan, on the other hand, is the weird one. It's opposite over adjacent, so tan is your opposite side, so y divided by your adjacent side, which is x. And believe it or not, you don't need to know this in great detail. That actually gives you the length of the line that connects where your intersection point is on your circle to your nearest x-axis. So it just tells you the length of that line, which is kind of interesting, but I don't think you'll need to know that quite yet. Now, even if it's not on a circle, these relations still apply, except instead of r, of course, you can just consider the length of the arm that connects the origin 0, 0 to the coordinate, right? So it's not your radius anymore, it's just the length of the arm that would connect to your coordinate. So this is the first thing that's going to be in that booklet, the note booklet, of course, that you can download off of Google Classroom. This is on page 26. It says, complete the following table involving all the points of intersection between the unit circle and the x and y axis. This is a note booklet. I just trimmed it down so it wouldn't appear on the slide. Basically, we're just looking on a circle. Hold on here. Like on a unit circle, I really should say. So if we kind of loosely draw a circle here, we're just looking at what the coordinates are at 0 degrees, 90 degrees, 180 degrees, blah, 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 as well as what sine of each of these values would be, as well as cosine and theta, of course. Anyway, if we look at 0 degrees, that's this point right here, your coordinate in that spot is going to be 1, 0. At 90 degrees, which is, of course, way up here, your coordinate would be 0, 1. At 180 degrees, which is right over here, it'd be -1, 0. 270s down there, that would be 0, -1. And then 360, it's kind of a dumb one to ask this. It's the same thing as 0 degrees, 1, 0. But you're going to see that there is a parallel between these two in just a moment again. Anyway, sine theta. As long as your calculator is in degree mode, it doesn't get easier than this. You just literally take in your theta right over here and plug it into sine, cos, and tan. We'll do sine first, then we'll do cosine, then we'll do tangent. We'll do it column by column. Sine of 0, if you throw that in your calculator, you're going to get 0. Sine of 90, you're actually going to get 1. Sine of 180, you're going to get 0. Sine 270, you'll actually get -1. And then sine 360, you'll get 0. Okay? We're going to start noticing a pattern here. If you're not noticing it already, I'll give you a hint. It has to do with what we just learned on that last slide. Remember, cosine theta. Of course, if you throw cosine 0 in your calculator, it's going to give you 1. If you throw cosine 90 in your calculator, you're going to get 0. Cosine 180 is going to give you -1. Cosine 270 will be 0. and then cosine 360 will be 1. Not a big surprise that that's the same as 0, right? Tan, of course, is a bit of a wild card. If you go tan 0, it actually gives you 0. Okay. If you go tan 90, you actually get an error in your calculator. I'll talk about that in just 1 second here. If you do tan 180, you'll get 0. Tan 270, you'll also get an error. And then, of course, tan 360 should be the same thing as tan 0. It is 0. So first, before I get to talking about tan here, I want to go back to sine and cosine. If you haven't already noticed it, remember, all of these values of sine are equal to the values of your y-coordinates. So remember, on a unit circle, sine is equal to your y. Cosine is going to be equal to your x-coordinates, right? So on a unit circle, cosine is just equal to your x. If it wasn't on a unit circle, it'd be equal to x over the radius of your circle, okay? Now, tan is a bit of a weird one, especially at 90 degrees and 270, but remember that tan is equal to opposite over adjacent, or in other words, y over x. Notice whenever tan has an error, x would have been 0. If you divide by 0, you're going to have an error. On a graph, of course, this is going to shoot up to either positive or negative infinity, but of course, on a calculator, or really just in general, at that exact specific point, you don't have a value of tan because you're dividing by 0, and that just doesn't work. So let's talk about the maximum and minimum values of sine and cosine. This is also on page 26. So what appears to be the maximum and minimum values for cosine and sine theta? Use words and an inequality to express your answer, verify your answer using a calculator, blah, blah, blah. Okay, well, we don't need to worry about the verifying your answer. It's pretty clear based on the table. For both sine and cosine, they're bound between -1 and +1. So I can even just say that in words. You can say both are always between -1 and +1. Now, if you're going to use an inequality to express your answer, you could say that -1 is less than or equal to cosine theta, which is less than or equal to 1, right? So in other words, cosine is bound between these two. And of course, we have to write it for sine as well. So we'll say -1 is less than or equal to sine theta, which is less than or equal to 1, right? So that's using an inequality. Now we can see that tan 90 degrees is undefined. What does this look like on your calculator? Well, if you say tan 90 in your calculator, it says error. But if you throw this in your calculator into your graphing mode, like if you actually graphed tan of x and then looked at where x equals 90 degrees, you're actually going to see a vertical asymptote. That'll be more important much later on. We don't need to worry about that right now. Just understand that tan 90 is undefined. And again, it's undefined because tan theta equals y over x. And at 90 degrees on a unit circle, 90 degrees right up here, x equals 0, right? So since you're dividing by 0, you're going to have an error. Okay, so this is actually what it looks like if you graph sine and cosine on a calculator. You could say that cosine theta, or in other words, cosine x, if you wanted to call it that. You know what, I will call it that. I'm going to cross it out and say it's x, and sine of x might make things a little easier. You could say that equals y, so y equals this, and y equals this. Both cosine and sine are actually going to be bound between +1 and -1. So I can just write them right here and right here, right? With 0 being, of course, in between on each of these separate graphs. Hopefully what you're noticing on this green circle here is that really your cosine x for your angle, right? So your angle is your x here. I'm kind of like making this more confusing than it needs to be. I'll correct this, hold on, don't worry. Your angle, as things go, it just spits out the x coordinate and the y coordinate. Now the reason when I change it here to say, oh, y equals cosine x, what I really mean is that's how you're going to put it in your graphing calculator, but it is still an angle theta. I'm kind of like digging myself a hole here by just saying that, but hopefully what you understand is that the value as your theta increases changes your cosine and your sine. Okay, anyway, we'll come back to that another time. That's kind of a horrible description, but kind of cool at least watching this graph go. You don't need to understand this quite yet, but just so you know. Anyway, for an example, this is actually where we actually need to go with this, so don't worry about that last thing. The point Q, -4/5 and 3/5, is on the intersection point between the unit circle and the terminal arm of an angle theta in standard position. Determine the exact values of the three primary trig ratios for theta. First thing I would do is I would actually draw this on the unit circle that they gave us. So -4/5 is my x. That's probably about right here, and then y being 3/5 being just above a half, I guess you could say. That's probably this point right here. And again, they called it point Q, so I'll do the same. So there's point Q. Let's connect it with a line as best I can. There we go. Determine the exact values of the three primary trig ratios for this. Well, of course, if we set this up as a triangle, a right triangle, I should really say, then it becomes a little easier to start setting up trig ratios for this. We know x is -4/5, and we know y is 3/5. As for our hypotenuse, we were told that this is a unit circle, so we know our hypotenuse is 1, okay? Let's start with sine. Sine theta is going to equal opposite over hypotenuse. So what we can say is the opposite side, being y, is going to be 3/5, and our hypotenuse is 1. But 3/5 divided by 1 can actually simplify down just to be sine theta equals 3/5, right? That would be an exact value for that trig ratio. And the reason that's useful is then you can use inverse sine on this to at least find your reference angle and then go from there. Now, cosine, on the other hand, is going to be equal to your adjacent side divided by your hypotenuse. And your adjacent side here is -4/5, and your hypotenuse is 1. Just like before, though, that's going to simplify down to cosine theta equals -4/5. The last one that we have to do here is tan theta. Tan theta is your opposite over your adjacent. In other words, your y over your x. Well, your y is 3/5, and your x is -4/5. Now, having a fraction over a fraction is a huge pain. Dividing fractions is not easy on its own, so what we do instead, or at least what I do, is I keep change flip. So in other words, I can say we'll keep the top 3/5, we'll change it from a divide to a times, and then we flip the bottom one, so then we make that 5/-4. This, of course, would simplify to be 3 times 5, which is 15, over 5 times -4, which is -20. But 15 over -20, notice 15 and 20 can both be divided by 5. I can actually simplify down to 3/4. And I don't like having a negative on the bottom, so I just move it up to the top. So -3/4. So just to finish that off, we'll say that tan theta equals -3/4. So that one causes a little bit more of a challenge, but not too bad overall. And I'll box all my answers here. So those are all your exact values for all three of your primary trig ratios. You could use inverse trig on each of those to get your reference angle. Again, what I mentioned the last day is I don't like using inverse trig on a negative number, so I would probably turn these ones positive before I did inverse trig. And then, of course, that just spits out your reference angle in here, which can then give you your true angle if you just take it away from 180 degrees or whatever other quadrant you're in, right? This also, just by the way, noting our answers here, it also obeys the old cast rule that we learned back in Math 20-1. That says the only thing in this quadrant, quadrant 2, should be sine that's positive. Both cosine and tan are both negative here, so that does follow that rule as well. So it's another indication that we've probably done this right. Now, what if I told you sine, cos, and tan aren't the only trig ratios? It's almost as if we've been kind of hiding the truth from you this whole time. There are actually more trig ratios than sine, cos, and tan. Let's cover them. These new trig ratios are called reciprocal trig ratios, and this is also on page 27. Before we do these reciprocal trig ratios, let me just recall that a reciprocal of a number is just 1 over that number. So there are reciprocals, so 1 over the number, for each of the three primary trig ratios. For our primary trig ratio sine, we actually have a reciprocal ratio called cosecant. Okay, I know it's a bit of a weird name. Don't question where the name comes from. We'll talk a little bit, well, not perfectly, but we'll talk a little bit about it in a second here. Cosecant's abbreviation, kind of like how sine's abbreviation is SIN. Cosecant's abbreviation is CSC, cosecant. And the ratio for cosecant is cosecant theta is 1 over sine theta, right? Cosecant is just the reciprocal of sine, okay? Next up, cosine. Cosine has a reciprocal ratio. It's called secant. Now remember, cosine's abbreviation was COS, cos, right? Secant's abbreviation is SEC, okay? Now the ratio for this would be SEC theta is 1 over cosine theta, because it's the reciprocal of them, right? That's how that works. Now tangent, of course, tan's abbreviation was just tan, right? The name of the reciprocal ratio, this is the only one that really, really makes sense, is cotangent. Okay, now cotangent's abbreviation is cot, C-O-T, and the ratio for that would be C-O-T, cot theta equals 1 over tan theta. Now, I mentioned before, I said there's not really a perfect way of like knowing which one was which. Here's how I always remember it. For all of your primary trig ratios, they always need a co. Now, cosine already has a co in front of it. So it doesn't need a co. It's a good co already, right? So it gets paired with a secant, but sine needs to get paired with the cosecant because sine needs a co. Now, you might be asking me right now, what about like sine being cosine? Yeah, I know, it's not perfect. Bear with me on this one, but it's just the way I always remember it. Sine needs to pair with cosecant, cosine needs to pair with secant, and tan obviously pairs with cotangent. And just so you know, I'm just going to pull out a formula sheet here real quick. Oh, yes, perfect. Thank goodness. All of these right here, all of these ratios in this box, those are all on your formula sheet. So you don't have to memorize them. You don't have to go, oh, it's cosecant with sine and all that. But it is just nice to know just offhand which one's which, so you don't have to always rely on your formula sheet, okay? Anyway, let's do a few examples. Referring to the example at the top of the page, and by the example at the top of the page, I believe they're referring to this one. So we'll even write it again. Q is -4 over 5 and 3 over 5. Determine the 3 reciprocal ratios for an angle theta whose terminal arm passes through the point Q. Well, here's what's nice. If we actually go back and we look at our sine, cos, and tan answers, we can just take the reciprocal of all of those for our cosecant, secant, and cotangent. Let me start with cosecant, CSC theta. Cosecant theta is 1 over sine theta. In other words, it's just the reciprocal of sine. If I go back a couple slides right now, you're going to see that sine is 3 over 5. That means cosecant of sine just needs to be the reciprocal of that. So the reciprocal of 3 over 5 is just 5 over 3. Okay? Now for secant, oops, there you go. For secant theta, secant is 1 over cosine theta. So it's just the reciprocal of cosine. If I go back and I look at what cosine was, we can see that cosine was -4 over 5. So logically, we just have to take the reciprocal of that and make it -5 over 4. And again, I put the negative on the top because I just don't like having a negative on the bottom. Now the last one we got to do here is cotangent. Cotangent of theta is just the reciprocal of tan. Now tan, we had a lot more work to do back then, but now that we've done that work, we don't have to redo all the work. We can just look at our final answer for tan and take the reciprocal of that. So tan was -3 over 4. So logically, cotangent would be -4 over 3. Those would be our reciprocal ratios. That's about all there is to it. Now, I'll be honest here, just up front with you. You might be asking me right now, okay, cool, we have these reciprocal ratios. What are they used for? That, unfortunately, doesn't have a very satisfying answer. Cosecant, secant, and cotangent on their own are not really super useful for applications like we would use for sine, cos, and tan. But cosecant, secant, and cotangent are quite useful when you get into calculus because they can make taking things called the derivative a lot simpler, right? So for now, just understand that you just have to see these as being the reciprocals. All right, I think this is the last question we're going to do today. It's on page 28 at the very top. The point -7, 5 is on the terminal arm of an angle theta in standard position. Notice this is not on a circle. It's just in standard position. It's just on your Cartesian plane. So if we drew a Cartesian plane, we're looking at the point -7, 5, which is probably about right here. I guess I'll just call it point P. It didn't give it a name. So we have that coordinate right up here. What is the exact value for all 6 trig ratios for theta? Okay, to set up these trig ratios, we still need to find an x, a y, and an r. R, of course, being your hypotenuse. X, in this case, is -7. Y, in this case, is 5. And then our hypotenuse, which is our r value, I'll just call it r for now, is currently unknown. But notice when we set it up like this, we have a right triangle. We could just use Pythagoras to find that. So 5 squared plus -7 squared equals r squared. That gives us 25 plus 49 equals r squared. Now 25 plus 49, I believe that's 74. Yeah, that would be 74 equals r squared. And of course, to get r, we have to take the square root of 74. Now, just remember, it's an exact value we're looking for. If you take the square root of 74, you're going to get like 8 point something. That's not an exact value. This is where it's quite nice in Math 30. You can actually kind of be a little lazy on this. You can just say r is just straight up the square root of 74, right? You don't have to actually like round it in any decimals or anything. That is an exact value. Just leave it as r is the square root of 74. So I'm going to adjust my diagram here. I'll just erase this and put in root 74 as being my hypotenuse. So just breaking this away now, let's find all 6 trig ratios here. We'll start with the simpler ones that we know from before. Sine theta is opposite over hypotenuse, or in other words, y over r. Well, that's going to give us 5 over root 74. That one is all taken care of now. We're done there. Cosine theta is adjacent over hypotenuse. Well, the adjacent side is -7, and the hypotenuse is root 74. So that one is now taken care of as well. Tangent of theta is going to be opposite over adjacent. Well, this one's not too bad either. It's just 5 over -7, but I'll write it as -5 over 7 because we don't like having negatives in a denominator. It just really looks quite bad. Those are our 3 primary trig ratios. We're looking for all 6 trig ratios. Once you have these 3 primary ones, though, the reciprocal ratios come very quickly, right? For sine, remember sine pairs with cosecant. Cosecant theta is therefore just going to be the reciprocal of this. So in other words, root 74 over 5. I literally just flipped it upside down. This next one, cosine, that pairs with secant. Secant theta is just going to be root 74 over -7. So I'll just put 7 down here and then I'll put a negative on the top, right? Secant is negative root 74 over 7. And then last but not least here, tangent, it's going to be cotangent theta equals the reciprocal of this. So 7 over 5, and we'll put the negative here on the top, so -7 over 5. That's it. That's all there is to those, right? It's just the reciprocal of the ones that we're already familiar with. Even though they're kind of new, they're still the same idea that we had learned before. Anyway, for practice, I want you to do page 201, questions 1 to 9, 13, and 19. Please give those a shot. If you need any help, send me a remind, send me an email, do whatever you can to contact me. And again, please check your emails daily and respond to any of the emails that I send. I do have to log all these, so please make that a little easier for me. Otherwise, I will be calling home. Anyway, if you have any questions, guys, please let me know. Talk to you soon.